Hi, welcome to Detours Understanding Acquired Brain Injury. And today I want to talk to you about a very key piece of equipment that is used in assisting in the diagnosis of brain injury and also used in research as well. And it's becoming more and more critical to help us to develop new treatments and to understand and with diagnosis. This piece of technology I'm talking about, of course, is the MRI, or magnetic resonance imaging or imager. The MRI machine is actually fairly simple to understand, and we're going to talk about the basics and talk about how it works. It seems kind of intimidating, especially when you get put into one of these things, but once explained, it'll make more sense as to what it does and to the way it works. Now, this is part one. We will talk about the different techniques and things that you do with an MRI machine, the way it can look at you, the way it looks at your brain in the second part. But I just want to talk about some of the basics of how the machine works. We talked about CAT scanners before, CT scanners, and basically a CT scanner is an X-ray machine on a spinning gantry that goes around your head, and it will pass low energy X-rays through you, and then it will use a receiver on the other end, which is sensitive to X-rays, and it will use a computer to build a three-dimensional image, and that's basically what it is. And it's in the computer where the real power lies. And the same is true as far as the computer being the real working part for an MRI. But it doesn't use ionizing radiation on MRI machine. An MRI is basically a very, very powerful magnet and a radio transmitter. And well, receiver as well. Can't leave that one out. But it's basically a strong magnet, series of strong magnets, and a radio transceiver. So let's get into it. First of all, the initial technology from which an MRI machine is built is based on something that they were working on in 1950s and early 1960s. It's called nuclear magnetic resonance. Nuclear in this case has nothing to do with radiation. It has to do with the nucleus of an atom. Atoms have three basic properties. They have mass, which is how much stuff. You can think of it as weight, but that's really not the right way to think of it. It's how much stuff is crammed into them. The more massive the atom, the kind of heavier it is, but really, it's like how much stuff. They have charge. Are they ionized? Is the atom ionized? Does it have a positive charge? Does it have a negative charge or no charge? Charge. Finally, something called spin. This is more complicated, but an atom, if you think about it as kind of like a top spinning, again, a little more complicated, but for our purposes, think of it like a top, okay? Spin. So mass, charge, spin. And these are the properties we're interested in when it comes to an MRI. A bunch of British and American physicists, engineers, scientists got together in the 50s, 60s, 70s, and were working with both NMR and some bright sparks and said, hey, wait a minute, we can use this to image the body. And they came up with a series of equations in order to apply the technology from NMR to apply it to the body. Now, they called it MRI because they were afraid that people would think that the N from nuclear meant radioactivity. World War II, the bomb, the things like 3 Mile Island and other incidents would make people afraid. They were probably right. But MRIs. So, what happens? Well, when you're being imaged, the big machine that you're put into is, the bulk of it is primarily the primary magnet. There are different ways to use this big magnet. You can make it a superconductive electromagnet. Now, what is that all about? what you want to do is cool down material that will act superconductive. So there are different materials. You can even use copper or whatever, but you chill it down really, really, really cold, like really cold. And you can use different ways of refrigerating it, but liquid helium, which is basically just taking gas from the air, helium from the air, and you put it under pressure, and you can liquefy it by doing that. And then you take this liquid helium, which is super chilled, and you use it, you pump it around, you cool down that magnet. And it allows it so it does not resist. Every wire, everything like that normally has resistance to it. It fights the electrical flow. Superconductive magnets do not fight that flow, and they become very powerful magnets. That's the typical and traditional kind of magnet, main magnet. There are also rare earth magnets. You've heard about rare earth metals before, I'm sure. You've heard about conflict materials, materials gotten from Africa or, in Asia, where people are literally fighting wars over getting these metals. But one of the reasons why they want these materials is because they make permanent magnets and very powerful magnets. Kids have swallowed these and have done damage to their bodies. They make toys out of these little magnets made out of rare earth materials. So when it comes to these kind of magnets, they have certain advantages. You don't have to chill these down. These rare earth magnets are incredibly powerful on their own. Primary magnet. And then you use a second kind of magnet called a gradient magnet. Get to that in a moment. Now, why do you want to put a person inside a magnetic field like this? The reason is because normally in your body, you have all different kinds of atoms, but the ones we're most interested in are hydrogen atoms. And the reason we're interested in hydrogen atoms is because water in your body is H2O, and we're interested in squishy tissues, fatty tissues, those kind of things that are harder to see than things you see with x-rays. And x-rays see mainly bone, things like that, but to see the squishy stuff like brain, muscle, intestinal, that kind of stuff, those connective tissues, the soft tissues, they're mostly water. And so looking at hydrogen really helps you see those kind of tissues. But hydrogen, remember how I talked about spin, that like top-like property? These kind of hydrogen atoms point all different ways. If left to their own devices, all your hydrogen atoms are pointing every which way. However, they are what's called paramagnetic, which means in a magnetic field, you will have these atoms pointing. But when you put them in a strong magnetic field like that generated by an electromagnet, all the hydrogen atoms in your body will point in the right direction, aligned. They will point in within the magnetic field. So, you've got a bunch of hydrogen atoms and boom, they're all pointed in the same direction. And that's what you want. All the atoms kind of like yelling recess in a large classroom or whatever, get all the kids to line up. It's the same thing with the hydrogen atoms. They'll all line up when put inside a powerful magnetic field. The reason this is useful is then you can do things with those hydrogen atoms to help you. Now, I said there's another series of magnets inside, and these are called gradient magnets, and their job is to slightly change just a little bit some of these atoms, just a little bit. While they're all lined up, you may just want to tip other different hydrogen atoms in your body just a little bit, and that's to help the MRI locate, based on the signal, get to that in a moment, where they are in your body. Okay, now these are the gradient magnets, and they help almost like a GPS system for the computer, but based on where the atoms are. Now what you're going to do is you're going to hit these hydrogen atoms with a radio wave. You're going to turn on the transmitter, and as these hydrogen atoms are spinning and aligned inside the magnetic field, you're going to hit them with a radio wave, which is going to cause the hydrogen atoms to take on extra energy. And it's going to cause them to flip into a different direction in which they're aligned. So hit them with a radio wave, and they will flip into an energized position. Now you turn the radio wave off, and they will do what's called precession. They will literally spin back into the alignment with that magnetic field. So hit them, and they spin down. Now, what's important about this is each hydrogen atom, it's like they have to give back the energy that they have. Conservation of energy. You can neither create nor destroy energy. You have to give back what you get. And so give them energy and turn the energy off, and they'll relax back. And this is called relaxation time. And you'll see this in some of your MRI reports. It may mention relaxation time and spin. Spin 1, spin 2, which is basically how much energy they're putting in. Now, the reason this is important is because their radio transmitter is all around you. The antenna's all around you. And they'll give you energy, and they'll listen with the receivers for the signal when it relaxes. Give them energy, give the hydrogen atoms in your body energy, and listen for it to come back. Give them energy, listen for it to come back. And the reason this is important is hydrogen atoms have their own radio frequency. So you give them energy, and they relax back. So, boom, relax. Hit them, come back. And these antennas are sometimes placed right over your face. If you've ever had that grid put over your head, that is a receiving antenna to listen for that sound. And the more hydrogen atoms you have, the louder and the more intense that signal. So, of course, that means more fluid, more water, more fatty tissue. And there's a very subtle change depending on how dense or how weak that signal is. It's almost like a chorus of singers. Louder, weaker, depending on where you're positioned relative to the singers. And the further back you are. And so naturally, your position will help you figure out, who's singing what. And that's what the computer's job is. The computer's job is to figure out how much fluid there is, how many hydrogen atoms there are, where they're located. And this is where those gradient magnets come in too. Because remember how I said that they put a little bit of a different tip on those hydrogen atoms. Even though they're all aligned, some of them just tweak it a little bit. And so their sound is just a little different. And so their radio signal will be offset by just a little bit. You can't hear radio signals, but the computer can with its antennas. And so it knows based on how strong or how weak and what frequency they have when they relax back. Hit them with the radio wave and they come back. But each one makes a slightly different radio frequency when it comes back. And the computer then will add up all these different signals. And this is why you need such a powerful computer, because all those different radio signals add up to different totals. And this is why it takes a while to build the image of you, because it has to sum up all those different radio signals, and then it will send this image to a video processor, and it will use that, which is a special type of computer to make images. And once it's summed it up, then it will send it to the computer whose job it is to make a three-dimensional picture. And it will use that using the radio waves that are released back from those hydrogen atoms to build a picture. So that is, in essence, how an MRI machine works. Now, you can listen for different types of atoms, not just water or not just hydrogen, but you can listen for water because water has a different mass. And you can listen for iron as well, which has a different mass because iron is heavier. And so as a result, iron will take a different amount of time. So if you hit an iron atom, it will move much more slowly and it will take much longer. And so iron's emission of a radio signal will be different sounding, and the frequency is lower, it is slower because its mass is heavier. And it's the same thing for water, is different, has a different frequency because it has two hydrogen atoms. And so when you hit water, it takes longer to come back into that magnetic field again. And this is how you build image. And you also are looking for different things. You may take a series of pictures, in effect, with radio imaging. And so you build almost like a small film. that is one of the advances now we're seeing, because the computers are fast enough now at summing up all those signals that you can almost make a movie of movement, for example, of changes. You can look at a beating heart. You can look at the flow of water, which is one of the techniques that we're using now to help image. And we will get into that later. But I did want to cover the basic mechanics of an MRI machine. It is a powerful magnet. It is a bunch of small magnets. And that is partly where the noise comes from, why you'll hear the loud, like, banging and screeching. It is, in effect, magnetic fields kind of fighting each other because you pump a lot of power into there. No, it's not going to tear itself apart or anything like that, but the resistance between the magnetic fields is often what makes that clicking and banging kind of noise. Plus, you got a lot of pumps in there in many of the older MRI machines because they need to be cooled down. So they have to pump the helium, and it's liquefied helium. It has to chill down the magnets. So you're hearing the interplay of these fields, these magnetic fields, and the high voltage electricity being pumped into the magnets in order to generate that signal that will flip the atoms and allow them to precess back into the magnetic field. And that's that term, when it relaxes back. And that, so just so you know, some of the mechanics of the MRI. So that is basically how it works. If you have any questions, please put them in the comments below. This is a little more technical than the CT scan, but what you can do with an MRI is so much more, because of the ability to identify different atoms and how they interact and what they can do. So, we'll be talking about the many uses of an MRI machine in the next video about this topic. So please click like and subscribe, hit that bell icon, and hope you have a good day. Bye.